Hello, everybody. Welcome to the last Game Changer seminar of this year of the International Space Science Institute, ISI. My name is Tilman Spohn. I am your host today. And it's a pleasure, to introduce Barbara Sherwood Lollar, who is our speaker today. Barbara is a university professor in earth sciences at the University of Toronto, and she's a specialist in life in the underground. She's a co-director of the Canadian Institute for Advanced Studies program Earth 4D, and I'm proud to say that she is co-chairing one of our ISI working groups on extant surface life on Mars. Barbara is highly regarded and has received a number of prizes, including the Killian Prize for Natural Sciences, the Gerhard Herzberg Gold Medal, Pedersen Medal for Environmental Geochemistry, and she has an International Helmholtz Fellowship that links her to Europe, and any award for protection of the environment. Today, she will speak to us about subsurface life on Mars and other planets in the solar system. And that is, of course, timely because we're all looking to finding life on other places. And subsurface life is, of course, of great interest here. Given the theory by Golds, I think that life may have started in the underground. But I don't know, maybe, Barbara, you will touch on that as well a little bit. Anyways, I won't take much more of your time. And please, Barbara, you have the floor.
Thank you very much. I mean, it's a great pleasure to interact with this distinguished group. I really want to thank you for the invitation, and so fortuitous in the less than 24 to 48 hours since all of the exciting news that's been coming out of both the TGO and as well the Perseverance rover missions about the latest information on water on Mars and organic matter on Mars. I think that really sets us up beautifully for some of the issues that we'll talk about today as we look at the lessons learned for planetary habitability beyond Earth from the investigation of subsurface life on this planet. And so you'll see as we discuss this, of course, there's many very fascinating areas in the subsurface study, including the marine lithosphere. But what we'll be talking about today actually relates to the deep terrestrial subsurface. And more specifically, what I'll be focusing on are our own studies and those of others throughout the world, focusing on the Precambrian crust. And there's a number of important reasons for that. One is, first and foremost, that in fact, if one looks at the continental lithosphere, more than 70% of the continental lithosphere is Precambrian in age. So there is a lot of old rock on this planet. And particularly as you go into the blue parts that you see here, these are the even older sections, the cratons. These are tectonically quiescent and amongst the oldest rocks on Earth. So they retain not only the history of our planet, on a 2, 3, 4 billion year time scale, similar to Mars, but they also are rocks that are inhabited by extant life. So they allow us to not only investigate the history of life, but also the possibility of extant life in the continental subsurface in billion-year-old rocks. And so with direct analogies then to the investigations and information that one might need to plan these missions from Mars. In our own case, we get into the subsurface through taking advantage of the vast network of operating mines, but also underground research labs that are located throughout the world in these rocks. A lot of our work taking place, in particular in the photographs you see here at the bottom, particularly both in Canada, and then work with T.C. Onstott and Esther van Herten and others and their groups in South Africa in particular. And I'll touch on some of the work from both of those locations today. This gives you a quick sense of what water deep in the subsurface continent of our planet looks like. This is a picture actually of T.C. Onstott, who of course we're still reeling from the loss of T.C. about a month ago. He's a giant in these fields. And so I love to use this photograph because this was taken 1.8 kilometers below the surface in the Witwatersrand Basin in South Africa, in one of the gold mines that we work at there. And what you see there is the phenomenon that we study, that is naturally occurring groundwater jetting out of fractures and boreholes within the subsurface. It's not, of course, we're down there because the mines provide us a way to get down there, but these waters are not a function of mining activity. They're naturally occurring phenomenon that's there in this environment. And in fact, what's fascinating is that if you talk to miners throughout the world, or for instance, as you'll see here, and take a look at the historical annals of the Geologic Survey of Canada, for instance, you'll see that the miners have known about this for over 100 years. And yet until the 1980s, this phenomenon largely ran under the radar of the scientific community, but in the 80s, and particularly in some cases, pushed not only by the development of the deep subsurface life programs, but also by the beginnings of the investigation of these environments in some places for potentially radioactive waste disposal. It was really in the 80s that big scientific programs began to really explore the nature of these phenomena in the subsurface. And as they did so, again, as you saw, they found water. The water is highly saline and sometimes actually brines, depending on where you are. It tends to be calcium sodium chloride dominated, with total dissolved solids, at least at the sites where I work, between 50,000 to 250,000. I'm sorry, that should be milligrams per liter, not grams per liter. The temperatures range from 20 to 65 degrees C, depending on where you are. And often when they're first encountered, they can be very high flow rates. As you'll see here, this is a discharge rate of gas actually from the boreholes of more than 18 liters per minute. But often that dies down over time. You'll end up with a much gentler bubbling, but nonetheless an ongoing discharge from these boreholes of both water and gas. If we take a look at what is involved in that gas, you'll see it's typically, because these are highly reducing anaerobic environments, these are typically reduced gases. And this picture is just here to show a quick example between the kind of thing we find in these environments. And I'm using a site on the Canadian Shield called Kidd Creek, here shown in solid white, and just doing a quick comparison to one of the marine systems, the Lost City hydrothermal systems, just to give you a sense of what the reduced gases look like. Essentially, both the hydrothermal vents and these deep cratonic fracture waters are amongst the most hydrogen-rich environments on the planet, with dissolved hydrogen concentrations on the order of 5 to 10 to 15 millimolar, which can account for up to 50% of the free gas volume. There are high concentrations of reduced gases as well, and particularly methane, ethane, propane, and butane at Kidd Creek, and these actually tend to be considerably higher than what one finds at the hydrothermal vents. And so you can imagine that if we find water and we find energy, there's a lot of interest in understanding the degree to which these energy-rich waters, the products of water rock reaction, can in fact sustain subsurface life cut off from the photosphere, cut off from the energy of the sun. There have literally, to this point in time, from groups all over the world, been dozens and dozens now of studies of microbial communities within these systems. We're beginning to understand something about the ways in which they're similar or different from the surface biosphere. But that's really only down to about 1 to 1.5 kilometers. What's fascinating is if you go deeper than that, there's still really only a handful of studies that have really characterized the most lean part of the biosphere, the places where there are the lowest cell counts, typically found in the deepest, oldest, and most saline waters. So I'm particular about places deeper than about 2 to 3 kilometers depth. What we do know about those, of course, came from a variety of studies, but I highlight here 2 of the earliest, which of course done by TC's group, where they identified a novel hydrogen-utilizing sulfate-reducing bacteria, Desulfurutus odax viator. And this sort of has become one of the iconic organisms that's cited when one looks at the deep biosphere within these systems. What's fascinating about these systems is the hydrogeologic isolation. And in fact, as an isotope geochemist, it's really understanding that geochemical energy, potential for water rock reaction and what it means for habitability, and putting that time scale on the systems. That's the key part of the work that we do at the University of Toronto. Essentially, these ancient rocks and fluids that preserve the products of water rock reaction, such as hydrogen, do so on very long time scales. Depending on where you are, close to the surface, you may be looking at groundwaters that are still in connection with the surface. As you go deeper, you may enter a regime in which the waters might be tens of thousands to even tens of millions of years old. And in a few very special places, we've actually now identified places where the fracture waters have mean residence times of more than 1 billion years. So showing us places where if there's life in those fluids, it's life that has been isolated on geologically long timescales. And this becomes important too when one thinks about extrapolating what we find here to other planets and moons, such as Mars, for instance, where the surface atmosphere may no longer be conducive to life. But as we all know, there's an increasing interest on investigating the subsurface for either biosignatures that tell us about extinct life or the possibility still of extant life on places like Mars. And so in particular, although I won't get into the details of the noble gas work that we do today, it's a critical part of this endeavor. We have done investigations in Canada, South Africa, Fennoscandia, and currently undertaking work in Brazil, where in addition to understanding the habitability of the fluids, a very important part is to put the constraints on of the noble gases. And that's because this allows us then to address what you see in bold and blue at the bottom of the slide. If one is interested in life in the subsurface, one needs to know not only what it is, but something about the timing of those ecosystems. How long have they been either in connection with each other or connection in the surface? Or how long have they been isolated and preserved, perhaps in the deep subsurface, cut off from the surface photosphere? And so that's an important component of the work we do. That said, in today's talk, because I want to talk about habitability, I won't be focusing as much on the timescale and noble gas aspect, but instead I'm going to focus on what we know about water rock reactions and the production of electron donors and electron acceptors that can drive habitability in the deep subsurface of Earth, and the way those new models of habitability are changing how we take a look at the potential habitability of other planets and moons in the solar system. The story really begins with the story of hydrogen. Again, it was back in the 80s when we first began to work in these environments. It was totally unexpected for us to find these levels of hydrogen. We just didn't have that understanding quite at that time. But we rapidly began to understand where all that hydrogen is coming from. And in 2014, I actually did a paper where we pulled together data from all of our work and other groups all around the world, about 350 different analyses within Precambrian rock to characterize where this hydrogen is found and to actually do an estimate of how much hydrogen is being produced in these rocks. And the key point is that was the first time that anybody had tried to do that for the continental lithosphere for the planet as a whole. We had lots of estimates for the marine lithosphere, but none had been done for the continents. And what was fascinating about that, the major take-home point, is that it turns out we were missing about half of all the hydrogen on the planet from water rock reaction, just by forgetting about the continents. So it's an important point to show that we really do need to take a look at all of these systems if we want to understand the full range of habitability. Certainly that paper doubled the global estimates of hydrogen production from water rock reaction, and specifically from two types of water rock reaction, serpentinization and radiolysis. Serpentinization has been known for a long time, going all the way back to the work in the 70s of Ivan Barnes. Essentially, ultramafic rocks, particularly serpentine, olivine, and others, when they undergo hydration through a series of joint reactions, produce hydrogen as a byproduct. This is now very well known and established. It's seen not only in the continents, but in the marine lithosphere at indeed places like the Lost City hydrothermal vent. And so essentially, it's not that big a surprise anywhere one finds ultramafic rocks, whether that's on the marine lithosphere, in ophiolites, or in the major gigantic terrains of ultramafic rock that exist on the Precambrian cratons. The Canadian Shield, for instance, consists of vast swaths of ultramafic rock called the greenstone belts. Anywhere you find hydrogen within that kind of a geologic setting or mineralogical setting, it's not really a surprise. We've grown to now, over the last 30 years, expect to find hydrogen anywhere we find ultramafic rocks. And so, for instance, if we take a look now and turn to the work that we've been doing in South Africa, again, with T.C. Onstad and Esther van Heerden and Tom Kieft and others through the years, if you're working up here in Zimbabwe, for instance, this is a picture of actually the ISSI used to advertise the talk. And it's actually perfect. You don't even know this, but my first drive to take the work we've been doing in Canada and move it to Southern Africa was because I had cousins volunteer teaching in a small, small town on the Great Dyke. And having gone to visit them and hiking the Great Dyke, I remember thinking, this is ultramafic rock. There has to be hydrogen here. So again, if you have ultramafic rock, it's not a surprise to find hydrogen. But when we began the work with TC, we focused on a different part of Southern Africa. We were working in South Africa specifically, and specifically in the gold mines of the Witwatersrand Basin, shown here on the map on the lower left-hand side in orange. And the thing about those sites in the Wits is these were not sites that had ultramafic rock. These were much more felsic sites. And so initially, TC did not expect to see hydrogen there. And so when we did, the very talented he's not young now, he's an established professor at National Taiwan University, Li Hung Lin. But at that time, as a PhD student, when he found hydrogen in the very felsic settings of the deep gold mines of South Africa, we had to think a lot further back to account for it. And in fact, all the way back to some of the initial work done at the turn of the century. There's a variety of different papers I can cite here, but it's fascinating to me that the 1910 treatise on radioactivity by Marie Curie not only discussed the effects of radioactivity, but also the effects of radiogenic reactions. At the time, what they called émanation radioactive, but essentially the effect on other elements, gases, liquids, and solids, of the production of alpha, beta, and gamma particles from radioactive decay. And so there's a fascinating series of chapters within that 1910 work. What Li Hung did was actually realize that radiolysis was the key to what he was finding in South Africa. And in a series of studies in 2005, using both laboratory experiments, some of which he did up here at the University of Toronto with us, using as well modeling and measurements from the field, he was able to show that the high levels of hydrogen in the Witwatersrand Basin were in fact related to radiolysis, the radiation émanative. Because of course, when alpha, beta, and gamma particles hit water particles, they break it apart, producing hydrogen as a byproduct. So depending on where you are, you may see the production of hydrogen from serpentinization, or you may see it from radiolysis, but the two together very much contributing to habitability in the deep subsurface, where microbial metabolisms that use hydrogen, in particular, coupling hydrogen to sulfate reduction, have found to be particularly important, and in some cases, dominant microbial metabolism. Serpentinization remains a very important process, but because of recent advances and recent discoveries, I'm going to focus the rest of today's talk on the radiolysis side of these discoveries, because there have been some very interesting things taking place over the last couple of years. Not only interesting things, but also, as I mentioned, the role of hydrogen utilizing, sulfate reducing microorganisms continues to be a real focus as we take a look at life in the deep subsurface on this planet. There is indeed a wide variety of metabolisms. I don't mean to imply it's the only one, but at site after site, we see evidence of, if we see anything, if we see life at all, we tend to see hydrogen utilizing sulfate reducers. And so there's a profound interest then, not only in understanding the origin of the hydrogen, which we've talked about to this point, but also in understanding the origin of the sulfate. And for this part of the story, I go to Long Lee. Long was a postdoc at University of Toronto. He is now a Canada Research Chair at the University of Alberta. And when Long began to think very creatively about this problem, he was interested not only in radiolysis as a way of cleaving water molecules to reduce hydrogen, but he was also very interested in understanding where the sulfate was coming that might support a deep biosphere of hydrogen utilizing sulfate reducing bacteria. And so he proposed not just to take a look at hydrogen, but to take a look at the sulfate. And in particular, what he found was, and if you think about it, it makes stoichiometric sense. When waters cleave to form hydrogen, of course, it also has to produce the oxides, and in particular, short-lived radicals, very reactive. And there's evidence in the literature that when that happens, when alpha, beta, and gamma particles, as you see in the schematic or cartoon on the right-hand side, when those are produced by uranium thorium decay and the water molecule is broken apart, you produce not only hydrogen, but also short-lived and highly reactive oxides. These have been shown in the laboratory by work by Lefterio and others that if it attacks pyrite, sulfide metal, that it can then oxidize the sulfate and release that sulfate to the fluids. And so indeed in his work, Long found exactly that, and he did that by sulfur isotopes. I won't go into great detail on the sulfur isotope side of things, except to focus on one particular thing. On the lower right-hand side, you see the rocks of Kidd Creek, and you see how beautiful they are. They're very rich in sulfides, in particular pyrite, and that's, of course, known more colloquially as fool's gold, but it's FeS2. And if you take a look at rocks that are more than 2.7 billion years in age, and take a look at something called the CAP33 value that's shown on the y-axis in both of these plots. That CAP33 value is a dramatic indicator of the age of a rock, because before 2.7 billion years, all rocks show a non-zero value, what's called a mass-independent sulfur signature. And it's indicative of aspects related to the Archean atmosphere. After the Archean and the oxygenation of our planet's atmosphere, as you can see here in yellow and blue, that settles down entirely and all the rocks have a zero value. And so if you're to measure the CAP33 value in the Kidd Creek rocks, it comes at no surprise at all to see that because they're from 2.7 billion years in age, back in the Archean, they have a non-zero CAP33 value. They have, as you can see, scattered down to about minus 0.02. No surprise there at all. That's the beautiful work by Jameson and Boz Wing out of McGill. And looking at the rocks, exactly what you'd expect. But what Long wanted to do was not to look at the rocks, but to look at the water. And when he did, and when he measured, so again, I'm showing you the values for the rocks here in black. When Long then in blue measured the waters, he found for the very first time a mass-independent sulfur isotope signature in something other than a rock. He actually found it in the dissolved sulfate within the fracture fluids, within the waters, showing us incontrovertibly that the sulfur within the water was derived from the ancient rock, and providing us then with an understanding that within these systems, radiolysis is actually delivering everything those microbes need. When you get radiolysis and it breaks apart the water molecule and produces hydrogen, the oxides then attack the sulfide minerals. And by that process then, radiolysis provides a coherent, long-term mechanism, even within ecosystems that are isolated from the surface, of continually supplying both the essential electron donor, hydrogen, and electron acceptor, sulfate. What's exciting about what's been going on recently is that we're seeing that this radiologically driven deep hydrogen and now sulfur cycle can actually be extended as well to the carbon cycle. And so it's that I'll focus on in the rest of today's talk, because again, that has important implications not only for deep subsurface life, but for prebiotic chemistry and astrobiology. To do this, I'm going to go back to the site where Long Lee did his work. This is a site which I've mentioned already, Kidd Creek. It's in the Canadian Shield at a depth of 2.4 to 3 kilometers below surface, and in rocks of 2.7 billion years in age. This is a site we've been working in since the early 1990s. And in fact, it's important to note that this was one of the sites where abiotic organic synthesis was first demonstrated, specifically in a series of papers where we were looking at methane, ethane, propane, and butane, as well as hydrogen within these rocks. So we've already known that this is a site in which the products of abiotic water-rock reaction, including abiotic organic synthesis, are powerful enough that we can actually pick up that signature of abiotic processes, even in the presence of the biological cycle. So it's one of the few places where we've got both abiotic organic chemistry and biological organic chemistry taking place at the same place. And earlier this year, we actually extended our work, not looking just at the alkanes, but extending that to look at acetate and formate that are found within those fracture waters, the same fracture waters where Long Lee did his work on dissolved sulfate. And what we found there was really fascinating. The first thing we should emphasize is if you know Precambrian rock, you know that it is not carbon poor. People tend to sometimes assume that, but that's not the case. There's lots of carbon in these systems. There's very large graphitic horizons. There are carbonate fracture minerals. What there isn't is low molecular weight labile organic carbon like you find in soils. So carbon's there, but the question is, what of that carbon is actually something that's bioavailable? And so to look at that, we tend to look at the DIC, the dissolved inorganic carbon in the fluids, which is typically quite low, as you can see here, 30 to 60 micromolar. If we look at the DOC, though, the dissolved organic carbon, there you see something quite interesting. First of all, it's not that low. It's thousands of micromolar, but it is a very unusual and very simple organic soup. If you look over here at the right at the figure, in orange is the total organic carbon in the dissolved fracture fluids. In blue is acetate plus formate. And so that you can see for most of these fluids, for some of them, it's entirely made up of acetate and formate. For most of them, it is at least 50% of the DOC. So 50 to 90% of the total dissolved organic carbon is made up of two things, acetate and formate. And that makes these some of the highest concentrations of acetate that have ever been reported, between 1200 and 1900 micromolar, and with comparable levels of formate. So a very simple, very rich organic soup, but a very unusual one. Just to compare it for a moment to other kinds of fracture fluids around the world, what we find here at Kidd Creek are very different from the organic acids one finds in sedimentary basin brines, in particular because of the very high levels of formate we see at Kidd Creek. That's rarely found in oil field waters. In addition, we see, as I've mentioned, acetate and formate and none of the other organic acids. And again, that's rare. In sedimentary basin brines, you usually find a lot of different organic acids, including propionate and butyrate, and we don't see those at Kidd Creek. Comparing these to what's found at the hydrothermal vents, there are significant differences as well. The hydrothermal vents typically have much higher levels of formate and very low levels of acetate, whereas here we have flipped entirely, and in fact, a 2-to-1 ratio of acetate to formate. What's interesting as well is because we've been able to go back to this site time and time again, we actually have an underground observatory there, we've been able to monitor both the concentrations and the delta C13 signatures of acetate and formate for over a decade. And what's fascinating is those are completely uniform. Nothing changes. Over 10 years, we have the same concentrations and the same delta C13 signatures. It's already perhaps showing us that this is an organic pool that perhaps is not being massively impacted by microbial activity. Where there's microbial activity using compounds like that, we typically see much more variation. But that's just circumstantial evidence. To move to the more specific evidence, this is work that we did with Verena Hauer and Kai Heinrichs at Bremen. They're, of course, some of the world's experts on taking a look at the acetate cycle in the subsurface. And this simply shows you in 2 slides, some of them, again, very important but unusual characteristics of what we find at Kidd Creek. Kidd Creek is shown in red. This is compared to a compilation from a review paper that Verena has done through the years at all kinds of other sites she's worked at. I've already mentioned that the Kidd Creek concentrations are amongst some of the highest concentrations of acetate that have been identified. As you can see by looking at the y-axis, in delta C13 signature, they are also unusual. They are the most enriched C13 values that have ever been reported for acetate, up around -5 per mil. They differ from other subsurface sites. If we take a look on the right-hand side here, what you'll see in the histogram is the delta C13 signature for graphitic horizons within Precambrian rock of the Canadian Shield. And as you can see, that has quite a range, but all of it falls within the typical range expected for ancient organic matter. That is that it clusters somewhere around between about -25 and -35 per mil. And there were many other sites, and at the top you'll see in blue called Thompson, another mine site that we work at. And there the acetate is very similar to that of the histogram below. The acetate's clearly coming from the rock. But again, at Kidd Creek, it's different. The rocks are the same as what we find at Thompson in terms of their delta C13 signature, but the acetate is not. The acetate, once again, is significantly more enriched in delta C13 signature. So at Kidd Creek, the high concentrations of acetate and formate, the predominance of acetate over formate in a 2-to-1 ratio, and the highly enriched delta C13 values for that acetate are all unprecedented in the literature. And as we struggle to try to explain this, Our colleague Benedict Menez at the IPGP introduced us to a series of colleagues in France who are actually doing some fascinating work on this from an experimental point of view. They're more physical chemists. Many of them are working in radioactive waste disposal, and they're looking at radiolysis as well. What's fascinating, though, is the experiments that they've been doing was taking a look not just at the production of hydrogen, but they'd also found that if you added calcium carbonate to the experiments, they were able to produce not just hydrogen as a byproduct of radiolysis, but a series of organic acids as well, specifically acetate, formate, and oxalate. The details of these radiolytic mechanisms and the production rates as a function of alpha, beta, and gamma radiation have yet to be completely elucidated, and none of the stable isotope fractionation factors have been developed yet. But certainly we've gotten very intrigued and in discussions with these groups in order to see if we can put together an experimental program that might begin to produce those kinds of parameters that would allow us to then really link up the significance of these experiments to what we see in the field. But at this point, we can at least do a plausible first order mass balance. You'll remember that Li Hung Lin did a whole series of papers in 2005, so we have a good estimate of the radiolytic production rate for hydrogen at our sites across the Canadian Shield in South Africa. If we link that up to the work that was done by the experimentalists, we're able to then predict from that hydrogen rate what the acetate and formate production rate should be. We're then able to do a first order estimate to calculate over a given time scale how much acetate and formate ought to accumulate. If indeed, as it seems to be the case, it's not being utilized, there's not a sink within the biosphere. That would predict, for instance, for the types of sites we have in the Witwatersrand Basin in South Africa that typically have residence times on the order of tens of millions of years, those rates would predict acetate and formate concentrations around 100 micromole, which is actually exactly what we find. In contrast, if we then jump to Kidd Creek, where we have these billion-year residence times, these simple calculations would predict that concentrations of acetate and formate ought to be in the thousands of micromole. And in fact, as you'll remember, that's exactly what we do find. These are some of the highest concentrations of acetate that have ever been identified. And that would be consistent with accumulation of those products of water rock reaction over these extensive timescales. And so just to conclude then, as you can see, one of the things that's happening is we're beginning to reevaluate habitability on Earth, or in the sense of extending our understanding of the variety of ways that life can sustain itself on a planet. And in particular, here suggestive that there's a possibility of habitable worlds sustained by radiolysis. Certainly within Earth, these radiologically driven deep hydrogen, sulfur, and now carbon cycles may sustain deep subsurface microbes in the absence of interaction with the surface photosphere. As my colleague T.C. Onstott used to call it, it may be important for us to think about the potential for the origin of life, not only in Darwin's warm little pond on the surface, but possibly we may need to look at warm little fractures as well, as life may either have at least plausibly originated in the subsurface as well, or it may be the product, of course, of colonization, the surface origin of life, and then a successive colonization of the subsurface. This certainly gives us new models for looking at planetary habitability and potential biosignatures, not just through the lens of photosynthesis. It's certainly part of a very important change in astrobiology right now that's beginning to ask, what would biosignatures look like if the planetary habitability model is in fact based on chemolithotrophic life rather than photosynthetic life? And it provides us with a way then of broadening our search for life to make sure that when we look at other planets and other moons and exoplanets, we're thinking about what biosignatures might look like if those are targets on which photosynthesis never developed. And again, like I say, extending then our thinking and our discussions with astronomers and exoplanet scientists about what really the full range of targets should be if we're searching for life within our solar system or beyond. And we're beginning to see this developing. Indeed, just to conclude with some future directions, as I mentioned earlier, there's a lot of people getting very interested now in hooking up across disciplines to probe reaction rates, preservation, fractionation factors, to begin to understand more about the breadth of water rock reactions, including radiolysis, that are important. Other groups, particularly in the prebiotic chemistry world, are doing some very important and intriguing modeling to look at extending these things to other cycles. So Adam et al., Pastorak, and even Ruta Carolite, who's a postdoc working with Chris Ballantyne and I at Oxford, are looking at modeling approaches to extend this to take a look at the way radiolysis may impact things like the nitrogen cycle as well. The interesting thing about radiolysis, as I mentioned this earlier, but I'm going to come back to it again, is that because it's controlled simply by the distribution of radioactive elements like uranium and thorium, radiolysis is less mineralogically restricted than serpentinization. As I mentioned earlier, serpentinization is very important, but it's restricted to places where you have significant mafic, but specifically ultramafic rock. In contrast, radiolysis takes place in all rock types because uranium, thorium, potassium are ubiquitous. And so in that sense, again, radiolysis might be particularly important for us to take a look at, as it may be a more universal driver of habitability and of potential abiotic chemistry. And Oliver Warr, working in my lab in 2019, actually did some analysis of that in the pictures that you see on the right, if you're interested in seeing the implications of that for looking at global habitability from radiolysis on our planet. In addition, of course, there are people who are taking this information and extrapolating it to Mars. And this is a study done by Jesse Tarnas. Jesse is with JPL right now, working on the Perseverance rover, and I'm sure very busy this week because of that. But he did his PhD with Jack Mustard at Brown and worked with us as well, and has done some interesting modeling, taking a look at extrapolating those radiolytic processes and rates of reaction to understand what they might mean with respect to the habitability in the subsurface of Mars. And then indeed, there are many groups that are looking at these actively in the context of understanding what might be the habitability of Enceladus, Europa, or even Titan, and developing mission planning around, again, this expanded notion of potential habitability models, both on Earth and elsewhere. And all of this fits very nicely into some work that we did a couple of years ago that I'm going to take a moment to just highlight here at the end. In 2017 and 2018, I had the great pleasure of working with 17 other colleagues across planetary sciences and astrobiology to pull together the Astrobiology Science Strategy for the search for life in the universe. And this report was released in the end of 2018. It's available on the National Academies website, and you can take a look at it. Essentially what it did was the 17 of us came together. We had white papers. It was still happily an in-person time, so we had delegations. We spent a year taking a look at the realm of activity and new ideas, theories, and observations, and trying to pull them together in terms of then pointing the way forward for where astrobiology might fruitfully go over the next 5, 10, 15 years. And one of the fascinating things about that is encapsulated here. In the end, we had 3 major themes in that report. One of those 3 we canonically called Go Deep. Essentially, what it points out is that 2 of the report's 9 recommendations all related to this need for a dedicated focus on subsurface processes and environments and dynamic habitability in the light of all of the various discoveries going on by groups all over this world and off. In the light of all of these discoveries from Earth, from Mars, from the ocean worlds and exoplanets, the report very strongly recommended this broader perspective that concentrated efforts to understand the subsurface. Now, it's important to note that doesn't just mean the capacity to drill. Drilling, of course, is important, but as we've already seen from the work going on Mars, from things like InSight, geophysical monitoring, from orbiters that can tell us about the subsurface, from taking a look at things like the methane measurements from Perseverance, which are intimately relied to processes going on in the subsurface, or in places like Enceladus or Europa, where plumes jetting off of these moons are delivering information about the subsurface to the surface. These are all a variety of mechanisms that we can use to understand the subsurface and thereby to better understand habitability models that are applicable on a more universal scale. For our particular research, just to end for a minute back on the work that we do in Toronto then, this is particularly why we find our focus on Precambrian fracture fluid analog systems, although we are earth scientists, why we find this so valuable in the context of astrobiology and planetary sciences. These kinds of fracture-controlled fluids give us important information about habitability and about how it is that energy gradients can be sustained on a planetary scale from fractured rock. Unlike many of the early work that took place and is still taking place in very high temperature hydrothermal systems, the continents allow us to look at a lower range of temperatures, right down to, in fact, areas that are ice covered. So we're able to look at things like hydrogen production from radiolysis and serpentinization and abiotic organic synthesis in much cooler places where there are much slower rates of reaction. But with the time scales, with hundreds of millions to billions of years time scales, allow accumulation of the products of those water rock reaction, even if the rates are sluggish. To return to the life question for a minute, one of the things these deep subsurface sites do as well is help us get away from contamination, frankly, and the terrible contamination of this planet that life has done for us. On the surface, of course, life has become so successful that the biological carbon cycle massively dominates. On the surface of our planet, looking for abiotic organic chemistry is literally like looking for the abiotic needle in a biological haystack. But as we go deeper into the earth, particularly into places like Kidd Creek, and I alluded to this earlier, Kidd Creek is a place where we know we have dominance of water rock reaction and abiotic organic chemistry, but we also have life. We've been able to show the presence of hydrogen utilizing sulfate reducers, but they're living at a very, very slow rates. And so in that place, we see a reversal of what we see on the surface of Earth. The surface of Earth, we have very high rates of the biological carbon cycle and very, very low rates of the abiotic carbon cycle. The deep Earth allows us to flip that signal to noise ratio, and in certain special places, take a look at places where abiotic organic chemistry still dominates, as it would have on the early Earth. And any signatures of life are, in fact, the biologic needle in an abiotic haystack. And that's a very handy analog for going to other planets where we may be looking at exactly the same thing. We're looking for a very small whiff of life on a planet that's otherwise dominated by geology. And then finally, of course, to come back to Mars and the exciting work that's gone on and been released over the last couple of days, as I mentioned, from both ESA and NASA and the other agencies. The work that we do in the Precambrian shields allows us to look at tectonically quiescent billion-year-old rock with mineralogical similarities, for instance, to Mars. And again, providing us with what was perhaps on Earth the best analogy we can get for a single plate planet like Mars, where we're looking at preservation of fluids and potentially of biosignatures on planetary timescales. As Tillman mentioned, we're currently with Jack Mustard at Brown. He and I are co-directing a major international, but also interdisciplinary team that's taking a look at what we call Earth 4D, where the third dimension is, of course, the subsurface, but the fourth dimension are these important aspects of time that I've referenced throughout the talk. And that group's called Subsurface Science and Exploration. Just a call out to them all here, and a photograph from one of our earliest workshops taken about 2 kilometers below surface in Sudbury, thanks to the deep subsurface physicists who operate the neutrino lab at that place. It's one of the few places where we can actually get such a large team underground, and certainly the only place where I can do an underground photo of that scale. So with that, I think I'd like to stop there, because I was asked to try to leave an abundance of time for discussion. I'm certainly happy to come back to any of the aspects that I've touched on and provide additional detail in the course of addressing any of your questions. Thank you.
Thank you very much, Barbara, for this fascinating talk. A really great talk. I think we learned a lot. There are certainly enough, a lot of questions. I have already some questions in the chat. I just wanted to briefly say that For the audience, you have two ways of asking questions. Either you write in the chat, and I will read the question then to Barbara for her to answer, or you can raise your hand and then, if you want, speak for yourself. I'd like to start with the questions that I have in the chat. So the first one was by William Ball. Do bacteria actively facilitate the reactions that produce the very H2 sulfates, etc., that they need to survive? So a feedback between life and habitability. Should I reread it or?
No, I opened up the chat so I can see it too.
Okay.
Well, I mean, I think the key thing is anytime you have the possibility of reactions, then likely those reactions are taking place. So the question is, is it a two-part one? Are things theoretically possible? And then do we see evidence of them? The second part then, seeing evidence of them, requires that whatever those reactions are taking place at a sufficient rate, that they impact the overall pool that we observe. And so I will answer that question in two parts. Obviously, once microbial ecosystems are there and active, of course, there is cycling. And if hydrogen is produced, we do have many sites where that hydrogen is in fact consumed. So if I'd wanted to, I could have focused on a couple of sites here, like Beatrix in South Africa, where we see that not only has life taken hold, it has begun to overprint the abiotic signatures. At Beatrix, for instance, the hydrogen levels have been driven way down. We also see the abiotic methane signatures have been deeply impacted by the addition of microbial methanogenesis. We also see, I think, in many of those sites, evidence for acetogenesis, which we do not see at Kidd Creek. So it all depends on the size of the pool. If the microbial ecosystem is large enough and dynamic enough, then they too get very much involved in the cycle. And yes, you do see their impact on in particular, as sinks of things like hydrogen and sulfate. The particular place that I focused on today at Kidd Creek, we don't see evidence of utilization of the acetate and formate by the microbes, but we do absolutely see evidence of them using the sulfate. That was actually a little bit buried. They asked me not to delve too much into the details of sulfur isotope geochemistry. So you'll notice when I showed you those sulfur isotope plots, I focused only what was going on the y-axis. Had I focused on what was going on the x-axis, I'd be able to show you that in addition to the production of sulfate by radiolysis, we then also see clear evidence of a second process. And that second process is exactly what your very insightful question has zeroed in on. We do see sulfur isotope evidence that sulfate pool initially produced by radiolysis is then drawn down by the microbial sulfate reducing bacteria present in the water.
Okay, thank you. Michel Blanc says, congratulates you for the talk, and then asks us, at Jupiter's moon, Europa, radiolysis, is provided for free by Jupiter's radiation belts. But could radiolysis of surface and subsurface ice at this moon or other Jovian moons generate the same kind of chemical disequilibrium you described for Earth? This may take a very different chemistry, or should we rather think of radiolysis at the ocean bottom of these moons in contact with the mantle or in the first kilometer of the mantle?
Well, the key thing with radiolysis, I think your points are very, very, on point for mineralogically constrained reactions like serpentinization. But radiolysis, of course, is going to take place anywhere where we have uranium, thorium, and other radioactive minerals. And so in that sense, the key issue is simply the presence of rocks that contain those elements. Where they are present, they will decay and they will produce alpha, beta, and gamma radiation as a function of that decay. The next question that might be very relevant, though, I think perhaps where you were really going with this is, then what kind of physical environment is a place where those products of radiolysis might accumulate to the point where they could actually produce a habitable environment. And there, the questions that you raise about whether or not that could happen within the ice, whether it could only happen within the ocean, whether it could happen only within the fractured rocks on the ocean floor, those are things that are still very much being investigated right now through models. But I think the process itself, I would say, must take place simply because of what we know about the distribution of the elements. Then the next question becomes, what's the best place where the products of those reactions might actually accumulate to the point where they would be significant with respect to producing a habitable environment. And there's still a lot of discussion going on about whether that would be in the ice, the ocean, or the rock floor underneath. I think all three are likely candidates.
Okay, thank you. I want to switch over to the raised hands. So Alexander Grossberg has raised his hand and wants to ask a question. Willie, can you give the microphone to Alexander Grossberg? Hello, can we have Alex speaking? Well, if not, then let me move back to the chat and maybe try it later again. Matt Griffin asks, could life have developed and evolved in the subsurface on Earth independently of life on the surface and remaining separated from it? If so, how could we search for such life, but not as we know it?
Great. Yeah, I mean, these are fascinating questions. I think if you think about the fact that we sort of consider the origin of life required energy, required a gradient or surfaces, and required water, liquid, then it is totally plausible that the original origin of life, to my mind, could just as easily have been in a warm little fracture, as TC would say, instead of a warm little pond. They both provide all of those opportunities. They provide fluid, they provide energy, they provide surface and gradients. The subsurface, in addition, provided, of course, some degree of protection from what was going on in the atmosphere at the time that life evolved on Earth. Now, that said, we don't know yet where life evolved, and it is very important to point out that although when one looks at the large amount of literature that's now been produced on the genomics and metagenomics of subsurface life, although that subsurface life contains many novel organisms, it also contains many things that are clearly related to other organisms we know already. And the closest comparison is, of course, what we find at the hydrothermal vents. So what's found at the vents is clearly genetically linked to much of what's found in the continental subsurface. So we have not to date found anything that would argue for a second origin of life. All the life found on Earth so far, in that sense, is life as we know it, or at least as we know it now in 2021. If there are any students listening, I always like to point out that when I was in high school, we didn't think there would be life at the hydrothermal vents because we were not paying attention to the potential for chemosynthesis. And so life as we know it is sometimes a changing spectrum. But certainly right now, what's found at the vents, what's found in the subsurface on the continents, clearly coming from a single origin of life, likely. They are more related than they are not. But that still leaves open the question, did life originate in the subsurface and colonize the surface, or did it originate in the surface and colonize the subsurface? Or did we have some interaction between those taking place on certain timescales? And I think that's entirely plausible. One thing that is clear is that it depends on where you are in the subsurface. Obviously, some parts of the subsurface have been undergone events, geological events that would have sterilized. For instance, if they were the subject of a meteor impact, that would not only have potentially life sterilized, a life-ending event for the surface, but could easily have sterilized significant components of the subsurface underneath. So one always has to look at the individual location in terms of the last time that life might have been viable in that place. But I think the key thing I would say is, although all of those questions are still open questions, we simply don't know, Matt has raised one of the most important questions that all of us continue to take a look at. We want to try to understand what's in the subsurface, how that relates to what's been found elsewhere in the subsurface, how that relates to what we see in the surface. And the hope is by eventually characterizing all of those communities, we can begin to say something more about the potential origin and evolution of life.
Okay, let's try Alexander Grossberg again. Alex, can you hear us? Do you want to speak? You have raised your hand. No, apparently not. Well, it's gone away now. Okay, so funny that this exhausts actually the questions well, there's another one. Are we drilling deep enough with Perseverance and Rosalind Franklin to find biosignatures on Mars?
Well, this comes back to really what we said in the astrobiology report, which is to emphasize that drilling is just one of a variety of different approaches. Both the Rosalind Franklin and the Perseverance, of course, are only really targeting the near subsurface, although we already saw from Curiosity how exciting it was that even the very short drills that Curiosity managed to do already showed us the transition from oxidized to unoxidized material. So it showed us that that transition was much closer to the surface than we'd expected. So any information from the subsurface is important, and the information that we will get from InSight, from Perseverance, from the Rosalind Franklin are all going to be fascinating. That said, there are other missions in development to try to go deeper, because obviously one of the key things would be, can we actually reach liquid water? That would be a fantastic opportunity, everybody is very excited about the development of those missions. So drilling is exciting. Drilling isn't fair. What we really try to encourage in the context of the astrobiology report is not to mistake the idea that drilling is the only way to get at the subsurface. Obviously, the measurements of methane in the Mars atmosphere show us that the amounts of methane are inconsistent with what we know of the lifetime of methane in the atmosphere. And the implication of the concentrations that have been found show us there must probably be a subsurface source. So that's subsurface information. Other places where we can get subsurface information are anywhere where the geomorphology, in fact, allows us in some ways to go deep. Gale Crater is something like 5 kilometers deep. It's already an excisement in the crust that allows us to get closer to deep subsurface processes. And as we've seen from the results from the TGO as well for Valles Marineris yesterday, it shows us as well that anywhere where we have gorges, where we have craters, where we have impacts, where we have cliffs or scarps, these are places where we may be able to get additional information where the subsurface processes are expressing themselves at the surface. Similarly, fractured terrains, like the South Pole of Enceladus, show us that large fractured terrains can also deliver material from the subsurface up to a point where we can even measure it by orbiter. So I'd just like to emphasize that drilling is an important part of it, but it's not the only approach to get subsurface information. There's a wide variety of different ways of going about this. Oh, here, Alexander, I think, has written his question.
Yeah, he's written this question. He asked for the link to the
right
that you just
okay.
mentioned. So I don't
Great.
know. You can write it right down or
dig it up. I have it. I'd have to just work at digging it up, but I can probably do that. I can probably multitask and take another question while I do that if you want.
Yeah, that's an interesting one here. Axel Brandenburg asked, have life forms with unconventional chirality of their biomolecules ever been found deep down?
Yeah, not to my knowledge. To the moment, to my knowledge, we're still working within the working parameters for chirality in the deep subsurface that we thought we had before. I'm not an expert in that. It might be good to talk to somebody like Steve Benner and ask him whether there's any new information on that front. But to my knowledge, no. So, as I mentioned earlier, so far, life that we found appears to be life as we know it. If we take into account the fact that life as we know it on a fundamental level. Obviously, we continue to find very different things. As I mentioned, we find novel organisms. This is obviously not our work, but I always point to the discovery of the Asgard archaea at the hydrothermal vents and the new information they're giving us about the potential transition from prokaryotic to eukaryotic life. The Asgard archaea was certainly not life as we knew it a couple of years ago. So within the spectrum that we have not found anything that requires a Star Trek type or weird life, it's all still obviously based on the same formulation of DNA that we know, and so far on the same chirality that we know. Nonetheless, there's been a lot of fascinating discoveries over the last little while.
Well, Andrea Kotrovia has put the link into the chat.
Oh, thank you. So I don't have to keep looking for it. Yeah, it's just on the, it was released some time ago, so.
I have a question, and I'm very much interested in interactions or the relations between plate tectonics and life. And I was just wondering, for radiolysis, would the higher concentration of radiogenic elements in the continental crust as compared with what we believe, we have in the Martian crust matter, for the question?
Oh, of course, all of these things matter. And then the function of time matters as well, right? I mean, if we take a look at the radiolytic models that have been done for Earth so far, they've been done based on modern day uranium, thorium, and potassium. And so there's interesting models that can be done both for Earth, running back in time, and then taking the concentrations that we know from Mars, for instance, and adjusting the models. But that has been done. The Tarnas et al. Paper, 2018, that I mentioned, the Jesse Tarnas paper, that's exactly what Jesse did, was to take the specific information for uranium, thorium, and potassium, having to extrapolate some of those, obviously, from the others, and porosity for the Martian crust to calculate the amount of radiolytic hydrogen that would be produced in that setting, and was able to show that indeed it can easily account for habitability in those environments. So yes, for each of these targets, obviously the models need to be adjusted to take into account variations in the elemental distributions, variations in the porosity. But so far it continues to show us that radiolysis is something that needs to be contended with. And to some degree, it's largely just a question of mass, right? It's a lot of continental crust, and even a small amount of uranium can produce a lot of hydrogen. When Li Hung Lin began to do his work, initially his hunch was that the hydrogen he was seeing from radiolysis must be related to the carbon leader in the Witwatersrand Basin, because the carbon leader in the Witwatersrand Basin is very uranium rich, in some places up to 10,000 ppm. So he initially thought, well, that's it. It's because this is such a rich hydrogen environment. But when he ran the models, in fact, he found out you can produce an awful lot of hydrogen from just the average uranium concentration as well.